I know what you're thinking. Watch out, Mr. Balfour. It's a snake. But it's okay, because this snake is made of Newton meters, which are a lot less venomous. Another thing it's good for is showing you guys how tension works. So tension is just the force that's created when something is stretched. So inside each of these Newton meters, there is a metal spring, and the more that's stretched, the more tension that's created. So if you look at the top, you can see this Newton meter, by the amount of white that's visible, is under quite a lot of tension, which makes sense because it's supporting the weight of all of these Newton meters below it. One at the bottom, very little tension, because it's not supporting any Newton meters at all. Now this notion of tension decreasing as you go down a line is very similar to what you guys will find in the exam at the end of the year. The only difference is that instead of a system hanging, there'll be a system that's being pulled. But it'll still be the case that the tension in each section drops off as you move away from the thing that's pulling. So I'm going to decapitate the snake and then show you a useful problem. Extensive health and safety has been assessed. Risk assessments all sorted. It's an X snake. Okay, here's your useful problem. Let's imagine that you've met the world's strongest man. There he is. And you've challenged him to pull a Eurofighter Typhoon, not to scale, and a trailer with a killer whale in it. As you would. Now, there are a few things that you'll be given in a problem like this. The pulling force of the world's strongest man, the frictional forces against the things that are being pulled, and the mass of each of the objects in question. And a typical question might ask you to find the tension in one of the cords. Let's pick this one, the one that's pulling the killer whale. Okay? Now we start off by noting that all of these things are connected. And if they're all connected, they're all going to accelerate at the same rate. Okay? If the world's strongest man was to accelerate more than the Eurofighter, then the cord would snap. So, we'll start off by just writing this for the total system. We can use the expression A equals F over M. And what is F? F isn't just pick any old force and hope that it works. I like the look of 5,000 newtons. I'll pop that in there. No, F is the unbalanced force. So I'm going to call that F-U-N, which gives you fun. Which makes sense, because physics is fun. So, let's work that out. So you've got 5,000 newtons. Take away the two frictional forces, 2,500, 1,500, and you're going to divide it by the whole mass that's moving, which is 19,190 kilos, giving you an acceleration of 0.052 meters per second squared. Think to yourself, does that make sense? That's quite a small acceleration, but then it is a man pulling a jet and a killer whale on a trailer. So, yeah, it's going to be quite small. Okay, now let's isolate this. We'll isolate the whale, because that's the part of the system that we're interested in. Even though it's actually a dolphin. That's another topic. So, a whale, we can actually start this by using the same equation that we used before. Fun equals mass times acceleration. But now we're just looking at the tail end of the system, So we just need to think about the mass of the wheel multiplied by how much it's accelerating by, and that gives you an unbalanced force of 417 newtons, rounded. Now, that is not the tension, so don't pat yourself on the back just yet. That is actually how much bigger the tension is than the friction. It's like the difference between the two of them. So to get tension, you're going to add your fun, unbalanced force, to the frictional force. And that will give you how much forward force you need to accelerate the whale, or the dolphin. So that's 417 plus 1,500 gives you 1,900, and again I'm going to round, 20 newtons. So if you're ever feeling tense about these kind of problems, just take into account friction and you'll soon be having a whole lot of fun